Good afternoon, everyone. I'd like to thank the organizers of this workshop for organizing this wonderful event and for inviting me. I'm excited to share some of the work that my group has done on theoretical methods and computational tools for machine learning. Let me start by a brief discussion of the motivation behind our work. Over the past century, we've seen remarkable advances in many areas, such as energy and transportation. For example, our legacy power grids are being transformed into smart grids to increase their efficiency, resiliency, and sustainability. And this transformation is based on using solar panels, wind turbines, smart meters, and new power electronic devices. We're also working on the design and implementation of intelligent transportation systems with driverless cars and automated highways. There are many other such networks that are being upgraded for the design of the smart cities. These systems have many sensors for collecting data, which are then passed on to mathematical algorithms for processing to gain knowledge about the underlying system. That knowledge is then passed on to some decision-making units to find the best actions for the operation of the system. It's clear that the operation of smart cities relies heavily on computational tools. And so we need to have computational tools that are reliable, meaning that they're robust to cyber attacks and sensor failures. And they're also efficient, meaning that they are scalable and can find the best solutions possible under tight deadlines and constraints. In this talk, I will discuss both notions of robustness and accuracy for machine learning models. First, I will talk about the issue of robustness verification for neural networks, and then focus on accuracy of our learning algorithms and discuss notions of global functions and restricted isometry. Neural networks are commonly used for the classification problem, where the goal is to train the classifier such that it can label the unseen data with high accuracy. Let's consider autonomous cars as an example. These cars are equipped with cameras which capture the traffic lights, signs, etc. in real time. So we want our classifier to label images with signs or traffic lights. But the problem is that not all images are accurate and perfect. They could be corrupted or distorted. For example, the weather could be foggy and affect the quality of the image. The sign could be damaged, or an adversary could attack the camera and corrupt the picture. If our classifier is sensitive, it may incorrectly label a sign. For example, in the autonomous car case, the classifier could classify the stop sign as a yellow sign or a red traffic light as green. Obviously, these are all very dangerous scenarios. But why do we use neural networks as classifiers? One reason for their popularity is that they can represent complicated nonlinear relationships very accurately. But the downside of these classifiers is that they are sensitive to adversarial perturbations and random noise, which could result in misclassifications. These are some famous examples of misclassifications by neural networks. They show that the small perturbations and noise applied to the images resulted in wrong predictions. Since predictions can be very sensitive to small changes in the input, we want to certify that our networks have robust decision boundaries. Each of these pictures show two different sets of points that are colored in blue and red. The left picture demonstrates a non-robust decision boundary, while the one on the right side shows a more robust scenario. A common threat model considered in such studies is that the possible inputs are in a convex polytope. We define a safe set of outputs, or correctly classified as the set of outputs that are on the left side of the hyperplane, which is defined by the normal vector C. And F here is the mapping defined by the pre-trained neural network. Since we want to show the worst case input in X is classified correctly, we maximize this function. And if the optimal solution is negative, in that case, we say the network is robust. Now, the challenge is that even when the input uncertainty set is convex, its output set may be non-convex because of the nonlinear mapping F. This certification problem is incomplete in general. And to overcome this issue, various relaxations have been proposed to over-approximate the output set by a convex set, and then perform the certification on the easier-to-analyze convex set. Now, if the convex relaxation issues robustness certificate, then you're good, and our true network is robust. But the relaxation error may make convex approach fail to certify. As you can see in this example, the true network is robust indeed, but the convex approximation is not. So we cannot make any conclusions about the robustness of the original network from this approximation. So our goal is to find tractable convex formulations with little relaxation error. Now consider a pre-trained K-layer ReLU network, where X is the input to the neural network, Z is the output, Z hat K is the pre-activation of the case layer, and W is the weight matrix. One of the simplest and most popular approximation classes is based on linear programming relaxations. As we can see in the top equations, the source of non-convexity is the ReLU activation function. We can relax the ReLU constraints to their convex upper envelopes, and this can relax the optimization into a linear program. But doing so make the feasible set grow significantly, which leads to large relaxation error. An alternative method that can reduce the relaxation error is semi-definite programming, or SDP relaxation. One SDP relaxation is as follows. We first introduce a new matrix variable P, which is in terms of the input vector X and output vector Z, and then rewrite the equations in terms of the variable P. If we drop the rank constraints, that becomes semi-definite programming, or SDP relaxation. SDP has less relaxation error than linear program, and it's been shown to usually have a zero error on one-layer networks. But the new variable P is high dimensional, and because of that, we cannot compute SDP for large networks. So we see that both linear program and SDP relaxations have their own advantages and limitations. Linear program is cheap, but is inaccurate. SDP has less error, but is computationally expensive. Our approach for solving these issues is to use partitioning scheme. We first focus on partition linear programming relaxation. We partition the input space into different parts, and then solve linear programming relaxation for each part separately. The advantage of this method is that we will have provably tightened relaxation. But now let's see when the relaxation is exact. In our approach, the input space is partitioned based on the rows of the weight matrix W, and based on this approach, the ReLU constraints become linear in each part as shown here. We showed that this partitioning results in an exact relaxation, and although this technique completely eliminates the relaxation error of linear program, using it in practice may be computationally intractable because it requires solving an exponential number of separate linear programs. To make the problem tractable, we ask ourselves, if we were to only partition along a single row of the weight matrix, which one is the best one to choose? This is an NP-hard problem to know in general. So instead, we minimize the worst case relaxation error, and this makes the problem tractable and also reduces the general relaxation error. Now let's talk about partition semi-definite programming relaxation. Let variable P be a solution to the semi-definite programming relaxation. If the relaxation is exact, meaning that the rank of the solution is 1, then these conditions hold. But note that these are just necessary conditions for exactness and not sufficient. Now, if we enforce these conditions in the optimization, that may help in pushing the variable P towards a rank 1 solution. But because of nonlinearity in variable P, semi-definite programming becomes non-convex. Instead, we developed a convex method based on these rank 1 conditions that can be used to motivate the SDP solutions to have a lower rank. In general, P may be written as V transpose V, where V is the matrix shown here, which is in terms of the input and output vectors. We can rewrite the rank conditions in terms of the new variable V and get a function that we call a G that serves as the measure of the rank 1 gap. If the rank is equal to 1, then this gap is equal to 0, and it's non-negative otherwise. Now, since this function is being equal to 0 is necessary for P to be rank 1, it's desirable to make this gap as small as possible. But the optimal solution, P, depends on the partition that we choose, and finding a partition to minimize this gap in turn depends on the variable P itself. To resolve this dependency issue, we first bound this gap by worst case upper bound, and then choose an optimal partition to minimize the upper bound. And this makes the partition design tractable and results also in a closed form solution. This table summarizes the benefits of partition linear programming and SDP relaxation over their unpartitioned versions for deep neural networks with various number of layers. The partitioned relaxation errors here are noticeably smaller than their unpartitioned counterparts. Okay, so for this part of my presentation, I'm going to discuss notions of global functions and restricted isometry. There are many learning problems that are converted to non-convex optimization, and also some key learning problems like training neural networks and matrix sensing with outliers are not only non-convex, but also non-smooth. But how can we deal with the issues of non-convexity for our machine learning problems? Well, we can use existing global optimization techniques like convex hierarchies to go around this issue. But the challenge is that these methods are too expensive and not scalable. And for this reason, data science and industry mostly rely on computationally cheap local search numerical algorithms. But how can we deal with the issue of having bad local solutions because of non-convexity? We call a local minimum that is not a global minimum a spurious solution. And there are many papers on spurious solutions for neural networks and matrix sensing. But they're mostly rely on ad hoc techniques to drive sufficient conditions for non-existence of spurious solutions. To study this problem systematically, we defined a new notion of global functions. We call it function global if it doesn't have a spurious solution in the entire space and is continuous. And these are examples of non-convex global functions. Now let's contrast the class of global functions with 4 well-known classes of functions. These are convex, quasi-convex, star, convex, and decreasing path. Note that the global functions include all these 4 classes of functions, but the nice properties we have for these 4 classes, like differentiability and a strictly decreasing path from every point to a global mean, break down for global functions. And there exist non-trivial examples that prove this. We've studied several properties of global functions and used them to study some important problems that appear in machine learning. One is tensor decomposition. Assume that we have a tensor of order D in terms of a vector Y, which is unknown. Our goal is to find Y based on incomplete information and noisy measurements. Each measurement is denoted as BI and is a product of some elements of Y plus some noise, for example, Gaussian. Some measurements could be subject to large corruption. Here, we use an L1 norm estimator instead of L2 norm because it's known that the L1 norm is a robust estimator that rejects outliers. This estimator minimizes the sum of absolute value of some monomials minus BI. We showed that the L1 norm estimator, which is non-smooth and non-convex, is a global function in the noiseless complete information case. We then extended this result to incomplete information with outliers in the matrix case and showed that positive robust principal component analysis has no spurious solution under some technical assumptions. As a reminder, robust PCI is about learning a low-rank matrix from the measurement of some or all of its entries, while some measurements could be completely wrong. To explain robust PCA, consider this matrix. In this example, unknown entries are shown in black and measured entries are shown in white. Each measured entry could be cracked, shown here with letter G, or corrupted, shown with letter E, but we assume the type is unknown. To analyze PCA, we map the locations of the G entries into a bipartite graph, and we do the same thing for the B entries. Now we consider the following regularized L1 estimator, and note that the unregularized formulation of this problem is commonly known as Montero technique. There are different smooth variants of this regularized estimator in the literature. For instance, Guy et al. Have shown that a smooth counterpart of this regularized estimator has benign landscape, meaning that every local minimum is global and every saddle point has a direction with a strictly negative curvature. But how about the non-smooth version? We showed that the non-smooth function is a global function, and the global minimum is the true solution if the bipartite graphs of the matrix satisfy some properties. One important application of matrix sensing is in computer vision. Tracking objects through video is a huge issue and is used in robotic navigation, autonomous driving, etc. And in all these scenarios, we are dealing with corrupted or noisy data. And when it comes to safety critical applications, we need guarantees on global optimality and robustness of our algorithms. Here, we want to detect the moving objects in these two videos. I should mention that the first video is a benchmark example in the literature, but the second video is recorded by my group on the campus of UC Berkeley. For both videos, we used a robust estimator and solved it using SGD. And we can see here that we were able to correctly find a global solution in the moving object. Now, let me briefly talk about the notion of restricted isometry. Let's recap the matrix completion problem first. The problem is as follows. We have a matrix with some known entries shown in blue, and the goal is to find the remaining entries. We want to make this matrix as low rank as possible and positive semi-definite. So if we decompose the matrix as XX transpose, we are looking for an X such that AXX transpose equals to B. XX transpose is the unknown matrix, B is the vector of known entries, and A shows what entries of the matrix is measured. Matrix completion is about having each measurement being a single entry, and this is a special case of matrix sensing where each measurement is a combination of some entries. The problem is formulated as a non-convex problem where we minimize some norm of AXX transpose minus B, and we could use L1 norm, 2 norm, or other types of norms. Now, to understand the non-convexity of this problem, let's start with an extreme case. That is matrix completion with full information. In this case, the operator A measures all of the entries of the matrix. So AXX transpose is the same as XX transpose. So the problem becomes really easy. We minimize some norm of XX transpose minus ZZ transpose over X. And it's easy to show that this objective function has benign landscape and there is no spurious solution. So if we can somehow relate the partial information case to full information case, we are done, because we know the full information case is an easy optimization problem. Now, it turns out that we can relate these through the notion of restricted isometry property. Restricted isometry property, or RIP, relates the norm of A of W to the norm of W through some constant delta. When delta is really small, that means that we can drop A and relate the partial information case to the full information case. And a recent paper in the ML community has shown that if that constant delta is less than 0.2, then we're good and the problem is easy. But we want to know how sharp this bound is. In previous approach, given some true solution Z and the operator A, we formulate an optimization problem and we want to see whether or not we have a spurious solution X. So here we search over the space of low-rank matrices. We came up with a new approach, which is as follows. Given some point Z and some point X, can we design an operator A that makes X a spurious solution for the problem? In that case, the search space is the set of linear operators. Then we can formulate the following optimization problem, and based on this, we showed that the sharp bound on RIP is not 0.2, it's 0.5. So every problem with RIP of less than or equal to 0.5 has no spurious solution, and for RIP greater than 0.5, there are counterexamples. But you would say, how conservative is RIP less than or equal to 0.5? What if we have a problem where RIP is greater than 0.5? There we can use prior knowledge, and prior knowledge means a good initial point for local search algorithms. RIP less than 0.5 means in the entire space there is no spurious solution. But when RIP is greater than 0.5, maybe we can say in a ball around the true solution, there is no spurious solution. It turns out that we can calculate the size of that ball where the radius of the ball depends on the RIP value. So RIP could be any number between 0 and 1. And as it gets closer to 1, this ball gets smaller and smaller. The region over which there is no spurious solution shrinks, and we need to have more prior knowledge. We also recently generalized these results to arbitrary nonlinear functions and the noisy case. Dialing back to the beginning of the talk, we are moving towards the smart cities where various networks in each city are being upgraded. The upgrade is happening on both hardware and software systems. We've had a lot of advances on hardware design, such as wind turbines and solar panels for energy systems and driverless cars for intelligent transportation. However, we need to have accompanying software to support the hardware and enable a safe operation. This needs advances in computational and data-driven methods for complex systems. The development of these methods is related to several topics in many different areas, such as optimization, control, algorithms, machine learning, AI, graph theory, and statistics, among others. And as a whole, it's crucial to improve the mathematical science behind machine learning and AI to make them useful for safety-critical societal systems. Before I end the talk, I would like to acknowledge my research group and my colleagues who were involved in different parts of this research. I would also like to thank the funding agencies listed here for their support. Thank you for your attention, and I'd be happy to take your questions.